All right, good afternoon. This is part 3 of our set of notes from Chapter 7, Pure Component VLE. And this set of notes will focus on the Clapperon Equation. So we'll derive the Clapperon Equation or go through the origin of the Clapperon Equation as it's presented in the text. In class, we'll derive the Clapperon Equation in a slightly different way as it's provided to you on my set of supplemental notes on the Clapperon Equation. My preference is to derive it using the dimensionless molar Gibbs free energy. Just find it to be easier and more straightforward, and dimensionless Gibbs free energy is going to be a term we'll use throughout the course in terms of generating new thermodynamic relationships. Okay, but we'll follow the presentation of the text, and we'll look at some useful results of the Clapperon equation and how we can use it. So again, we'll follow the derivation of the Clapperon equation from the text. You can download my supplemental notes. The link will be provided, with this slide and also on our course Canvas page, so you can see my alternative derivation using dimensionless Gibbs free energy, which is what I would prefer because we'll use dimensionless molar Gibbs free energy throughout this class. Okay. And so the general idea behind the derivation of the Clapperon equation is for our system at binary vapor-liquid equilibrium, we have equality of temperatures, pressure, and molar Gibbs free energy. Okay, and I'll say vapor-liquid coexistence, but we could perform the same derivation for, say, solid-liquid phase equilibria. Okay, so I have two phases of coexistence at the same temperature, pressure, and molar Gibbs free energy. So we'll let phase 1 and 2 will designate our phases. So we have equality of temperatures, pressure, and molar Gibbs free energy. And since the molar Gibbs free energies are equal to each other, we could equivalently say that the differential of the molar Gibbs free energies are also equal. So the derivation as presented in the book begins as differential of molar Gibbs free energies are equal. Let's plug in our fundamental equation for G. Okay, so I plug in my VdP minus SdT, where V and S correspond to the value of V and S in each phase. Okay, P and T are the same in two phases, right? So it's just call it P sat and T. And then next step is P and T, are the same in the two phases. We just collect terms and then rearrange. Okay, so we get that dP dt is equal to delta S over delta V. Okay, and so next we're going to work on getting rid of this delta S term here. And so how we do that is we go back to our definition of G. Okay, so at coexistence, G1 is going to be equal to G2. Our molar Gibbs free energies in the two phases will be equal. So we have equality of molar Gibbs free energies. And so next, I plug in for G my definition of G, H minus Ts. Temperature, again, in the two phases are equal. So once again, we're going to rearrange and collect terms. And we get that delta H over T is equal to delta S, or for the particular case of vapor-liquid coexistence, delta H of vaporization over T is equal to delta S of vaporization. So if you go back and plug that in, we have that dP dt is equal to delta H over T delta V. Okay, so this is for the case of vapor-liquid coexistence. Okay, so if I look at this expression, this is our general equation. So if we weren't looking at, say, vapor-liquid coexistence, you could work out the same expression for, say, solid-liquid equilibrium, right? You could get an equivalent expression for that two-phase equilibrium. So here's one form of our Clausius-Clapeyron equation, our Clapperon equation. And then what we'll do next is we'll just simplify to get rid of delta Z of vaporization. So delta Z, or delta V, is equal to RT over P times delta Z. Okay, so remember, equation of state for real fluids is PV equals ZRT. So V is equal to ZRT over P. Well, temperature and pressure in the two phases are equal to each other, and that's how we get delta V is equal to RT over P delta Z. Okay, so I could substitute in. Okay, and then the other relationship we take advantage of here is we play around with the differential of log and our quotient rule to simplify this expression. So in terms of just introducing log P and then introducing log P and inverse T. Okay, so if I look at, say, this form, d log P d inverse T is equal to negative delta H of vaporization over R delta Z. Okay, cool. So this is our Clapperon equation. All of these boxes in red are equivalent ways to write the Clapperon equation. Okay, this box in yellow is just the math tricks needed to go from the first red box to these later two. Okay, cool. So next, we'll look at what's called the Clausius-Clapeyron equation. So going from Clapeyron to Clausius-Clapeyron, Clausius-Clapeyron just makes some assumptions to simplify the equation. Okay, so the assumptions, the first main assumption we'll make with the Clausius-Clapeyron equation is that we're at low pressures, so we're removed from the critical point, so that the vapor phase can be assumed an ideal gas, and that the molar volume of the liquid is negligible compared to the molar volume of the vapor. Okay, so let me pause and repeat this one more time, because this is a common source of confusion. We've said so far that all fluids approach ideal gas behavior in the limit that P goes to 0 or V goes to infinity at constant T, right? If I'm riding along an isotherm. Okay. Here we're looking at vapor-liquid coexistence. So now the idea is that at low pressures, okay, so if I'm at low pressures, then my vapor phase or my phase can be considered an ideal gas. Okay, so we're just talking about low pressures altogether. So if I think about my P versus T phase diagram, so if I'm writing down my equilibrium curve, so again, essentially it's in the limit that P goes to 0 at low pressures, we're assuming that that vapor phase in equilibrium with the liquid can be treated as an ideal gas. Okay, so in doing so, right, so we'll say that delta H of vaporization would be equal to the molar volume of the vapor relative to the molar volume of the liquid. Okay, well, the vapor could be modeled via the ideal gas equation of state, RT over Psat, and we're assuming the liquid volume is negligible compared to the vapor phase. So essentially we're assuming that it's 0, it's negligible compared to that molar volume of the vapor. And equivalently, we could write this as, delta Z of vaporization is approximately 1. All right, so vapor phase is an ideal gas, and liquid phase is essentially 0, right? Its molar volume is negligible compared to that of the vapor phase, okay, which can be treated as an ideal gas. So with those simplified assumptions, we essentially kill delta Z of vaporization, and we get that d log P d inverse T is equal to negative delta H of vaporization over R. Okay. So this is our Clausius-Clapeyron equation. Okay. And so then next, we can separate variables and integrate. Okay, so you get that log Psat is equal to log P naught sat, some reference pressure, minus 1 over R, integral from 1 over T naught to 1 over T, delta H of vaporization, d inverse T. Okay, cool. Okay, so we'll go more into integrating this term on the next slide. Okay, but even at this, right, what this tells us is that if I'm looking at my P versus T phase diagram, okay, the slope of my equilibrium curve, okay, d log P d inverse T, the slope of that equilibrium curve is going to be related directly to enthalpy of vaporization. So directly from that P versus T phase diagram, if I can differentiate or estimate the slope of my equilibrium curve, that gives me an estimate of delta H of vaporization. Cool. And delta H of vaporization can be used as a measure of the intermolecular interactions in my system. Right? So especially in this case, if I'm going from a liquid to an ideal gas, in an ideal gas, molecules don't interact. In a liquid, intermolecular interactions are really, really important. So if I'm vaporizing something by taking it from a liquid phase to an ideal gas, that's essentially accounting for or giving you a measure of the intermolecular interactions in my system. Cool, right? So, if you wanted to compare intermolecular interactions in two different phases, right, that could reduce to, if I measure enthalpy of vaporization, I could compare the two. The one with the larger delta H of vaporization, the one with the stronger intermolecular interactions. Okay, the one with the stronger intermolecular interactions will have the larger slope on my P versus T phase diagram. So the rate of change of pressure with respect to temperature is going to be larger. Cool. Okay. But anyways, so getting back to integrating this, in order to integrate this, or what this tells us is to calculate log P. If I know the value of log P at some reference temperature, I can then integrate delta H of vaporization from that reference temperature to my temperature of interest to calculate log P. Okay. In order to integrate this, I need to know how delta H of vaporization changes with temperature. Okay. So in theory, we could say calculate this using a cubic equation of state. We saw how we could calculate it using Watson's equation, and corresponding states theories also exist, right? And so if you were faced with having to integrate this, again, look at Chapter 7 of Properties of Gases and Liquids by Pulling, Proudus, and O'Connell, and they'll give you some recommendations. Okay? And then at least this year in class, we'll play around with actually evaluating this with Watson and compare that to just assuming delta H is constant in class. All right, so one simplification that you can use to arrive at a simplified form of the Clausius-Clapeyron equation is to simply assume that delta H of vaporization is constant. Okay, or more formally, over the specified temperature range, we're going to assume that delta H of vaporization is constant. Okay, and in the limit that delta T goes to 0, right? This is a reasonable approximation. As the temperature range increases, then this becomes much more of a stretch. Okay, but if we assume that delta H of vaporization is constant, we can pull delta H out of the integral. Okay, and so then we just have the integral of d inverse t, and we arrive at the relationship that log p sat is log p naught minus delta H of vaporization over r times 1 over t minus 1 over t naught. Okay, so log p naught is just a constant, it's my reference pressure. Delta H of vaporization over r times 1 over t naught, well, t naught is just my reference temperature, it's a constant. Delta H of vaporization over r, delta H we said is we're assuming it's constant, so it's just a constant. Okay, and so we can group those together into just some generic constant A. And then we have delta H of vaporization over T, right? And we can group that into this common B term over T. Okay. And so by assuming delta H of vaporization is constant, okay, we arrive at the expression log Psat is equal to A minus B over T. Okay, and let's again summarize how we arrived at this expression. We started with our rigorous expression for phase coexistence, right? So equality of molar Gibbs free energies. We then, plugged in definitions of G and differential of G, and we arrived at, the Clapperon equation, which is rigorously correct, right? And we boxed it in. Okay. The issue with the Clapperon equation is actually working with it. All right, it had a term in there, delta Z of vaporization, and we had delta H of vaporization. And so if I wanted to get, say, log P from said expression or solve for log P, I would need to know how both delta H and delta Z change with T. Okay, and that may not be readily available. So we made some simplifying assumptions to allow us to readily generate an expression for log P. Okay, we assume that molar volume of my vapor phase, or molar volume of my liquid is negligible to the molar volume of the vapor, and the vapor phase was an ideal gas, which led us to delta Z of vaporization is just equal to 1. And that assumption is, in general, pretty good as long as we're removed from the critical point. And then the second major assumption was that over narrow temperature range, delta H of vaporization is constant. Okay, and that led us to this final expression. Okay, so we started with the rigorous thermodynamic relationship and made some simplifying assumptions. Okay, but what this will give us is actually quite powerful, right? This tells us that log P should scale linearly with the inverse of temperature. Okay, and we'll look at some actual data in a second, and we'll find that in general, log P does scale with the inverse of temperature. Okay, and this is such a powerful relationship that it's very common when I plot my P-T phase diagram, rather than plot pressure versus temperature. And we saw that figure in the book, right? We had this exponential relationship. Okay, this suggests plotting log P versus inverse T to linearize our data. And by having linear data, it becomes much easier to interpolate and extrapolate. Okay, and so starting with our fundamental equations, we are able to gain some insight into how we expect pressure to change with respect to temperature. Okay, and we'll look at that again, as I said, in a second. Okay, it also gives us some insight in terms of how to develop useful engineering relationships. Okay, so our Clapperon equation, once again, assumed that vapor phase was an ideal gas, molar volume of the liquid was negligible compared to the vapor, or equivalently the delta Z of vaporization is equal to 1. Okay, so that's a reasonable approximation, well removed from the critical point. Okay, the bigger approximation is we assume that the enthalpy of vaporization was constant. Okay, and so we'll find that use of the Clapperon equation is going to be useful at low pressures and over narrow temperature ranges. Okay, low temperatures where this ideal gas approximation is good, and then over narrow temperature ranges, right? So the limit that essentially delta T goes to 0, this delta H of vaporization is constant approximation becomes essentially exact. Okay, so cool. So this is our Clausius-Clapeyron equation. Right? So if I have this equation and making these assumptions, I get this functional form. Okay, and we say, okay, that's good. Okay, that's great. We see that our vapor pressure data does follow this sort of scaling. But in terms of making accurate predictions, it's not quite as good as you could want. Right? What do? Well, we start with this physically based model. Right? This model is physically based. It has some fundamental theoretical origin, and we tweak it. Okay, and so here's my Clapperon equation. Okay, on the line below it, here's a form of the Antoine equation, which you've probably used at least in your mass and energy balance class. Okay, and so if I compare the Antoine equation to the Clapperon equation, they look very similar. Okay, the difference is in the denominator, right? So instead of b over t, we have b over t plus c, right? We stretch our temperature axis, right? Cool. All right, so all we've done is we've introduced a third parameter, and what we find is with the addition of this third parameter, we greatly increase the temperature range for which this expression is applicable. Right, and hence, the Antoine equation is a very common way to correlate vapor pressure data. Right, but its origin is based off of the Clausius-Clapeyron equation. Excellent. Okay, when you see the Antoine equation, you may see this log base 10, but change of base would just be multiplying everything by constant. Right, so it's straightforward. Okay, so a little more of a stretch, but kind of the, the gold standard in terms of correlating vapor pressure data, if you have enough data, is the so-called Wagner equation, which correlates with respect to the log of my reduced pressure, and use this parameter tau, which is 1 minus the Roos temperature. And so as long as you have sufficient data to correlate these 4 parameters, Wagner can actually work from your triple point all the way up to your critical point. Okay? And Pauling, Prositz, and O'Connell, they have some values tabulated for those. Antoine, seems to be a lot more, a lot more common if I look in terms of handbooks and correlating, binary VLE data, and also the back of your book for pure component VLE. It's just oftentimes, Antoine's not going to take you all the way from the triple point to the critical point. So it's very common that for a given fluid, you'll have, say, 2 sets of Antoine constants with 2 different ranges. But in general, that's easy enough to code up that, if in this range, use this value. If you're in that range, use that expression. Okay, and so just to give you an example of some data. So this is some data downloaded from NIST thermophysical properties for water. And so here's my standard P versus T phase diagram. So I have pressure in bars versus temperature. And I'm going all the way from the triple point, which is essentially 0 degrees C. So if you go from the triple point all the way up to the critical point, all right, we see that our data is essentially exponential. Okay. What I've done on the next slide is, so all I've done is label the triple point. So triple point's it's 0.01 degrees C, so essentially it's 273 Kelvin. So, that's 250. Actually, it's, more over here. Okay, here's my critical point. Okay. So, our Clausius-Clapeyron expression suggested a scaling of log P with inverse T. And so we find is if we plot this in a Clapeyron plot, where Clapeyron plot is just log P versus inverse T, that our data actually, it's fairly linear. And if you look carefully at it, there is some curvature to the data, but compared to where we started, all right, this is much more straight. Okay, and when I'm dealing with data sets, data set that falls on a straight line is always a good thing. Why? Because it becomes much easier to interpolate within that data set if I need to fill in gaps or find values at conditions where points are missing, and it also becomes much easier to extrapolate within a certain limit. Okay, and so this might even suggest that in the absence of anything, if I just had, let's see, if I had 2 reference points, I could fit a Clapperon equation, right, A minus B over T, which would do a pretty good job in terms of estimating vapor pressure over that entire range. Of course, it would be better if I had a 3rd data point. I could fit an Antoine equation, and if I had more than that, then I could fit a Wagner equation over that entire range. Okay, but just by starting with our fundamental equation and getting to the Clausius-Clapeyron equation, we gain insight into how best to model vapor pressure data. Right, log P versus inverse T is key. Okay. All right, so again, this is all the way from critical to triple point. So another common way, just in case you see it, is in this case, instead of having 1 over T, I use an inverse T axis. So this is an inverse axis, and I could take P and I could plot it in a log axis. But again, the effect is to linearize it. This is kind of old graph paper, for lack of a better word, so might not be as common, in your everyday courses, but such types of graphs would still exist in handbooks that you might encounter. Okay, and that's the end of the the set of notes. And so with that, we'll move on to the next set.